Let's now talk about a little bit trickier thing. Let's calculating equilibrium concentrations if I knew what the K equilibrium constant value is. Can I use those ice tables, but now rather than calculating K, I'm going to determine the equilibrium concentrations. Again, we talk about these ice tables. They create an algebraic expression of K in terms of X, the moles of reaction. Again, X, I don't know. I don't know how much this reaction proceeds before it reaches equilibrium. But I can use these and mathematically solve for X if I know what the equilibrium constant value for the equation is, for the reaction is. So I can then plug that back into the equilibrium constant expressions to figure out what the equilibrium concentrations are. All right, so I do need to remind you, because sometimes this gets a little uglier with we have some coefficients in here. Sometimes we have x squared terms. So quadratic formula review. When I have a second degree single variable polynomial written in standard form, in other words, when I have a quadratic formula, ax squared plus bx plus c. Note that these a, b's, and c's don't have to be coefficients. They could be just any numbers. But if I end up with an algebraic expression of that equals to 0, so now I've rearranged it to be in that standard state, then x will be equal to the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over the denominator of 2a. So if I know what a, b, and c are, so I have to get it to the point where I have a standard quadratic formula, then I can actually determine what x is using the quadratic formula. Now, obviously, if I have a second degree polynomial, then I'm going to have two solutions for x. One in which case I add the plus and the minus, so I get two roots. However, now, because this is related to a chemical reaction, I can use some ideas often to reject some of them. So oftentimes there's only one possible value of x in terms of the conditions that we have based off this being a chemical reaction. So the change in the moles of reaction can't be an imaginary quantity. So if I end up with complex roots with a I in it, can't be. Doesn't mean it's not a solution to this. It means it's not physically possible for a chemical reaction. Additionally, the change in the moles of a reaction cannot result in a negative equilibrium concentration. When I'm done, all concentrations must be positive values, right? Like you can't have a negative concentration. So if I get a value of x that results in a negative equilibrium concentration, then it's not possible. So oftentimes, although I get two roots, very frequently, one of them can be eliminated as being an impossibility. We're going to use the small x approximation a lot because it makes the math a lot easier. Okay, let's just look at some reversible reaction. So let's say that I know this would be related to, I know an equilibrium constant value, and I've set up the ice table, and I get some expression like this. 1.6 times 10 to the negative 8 equals x squared over 0.15 minus x. Now, realistically, I can't solve this without using the quadratic equation because this is not going to equally cancel out. But if I say, what if this x was really small compared to 0.15? Like it's 0.000001. 0.15 minus 0.000001 is still pretty much 0.15. It's not going to change the value of that. If I say that because x is so much smaller than what it's being subtracted from, then this reduces now to 1.6 times 10 to the negative x squared over just 0.15. I can use simple proportional algebra to get this, right? I just multiply both sides by 0.15, take the square root of both sides, and I can solve this one. So this one's way simpler. I don't have to use the quadratic equation. However, I can only do this if x is much smaller than 0.15. And I'm looking at this specific case. So we will use this small x approximation if less than 5% of the limiting initial reactant reacts. It is appropriate to use this approximation. So chemists have just made 5% the magic number. If x is less than 5% of the initial concentration, then we say, yeah, then this is a fair approximation. It will get you close enough to the right answer that, even though realistically the right answer would have to use the quadratic equation. This will get me close enough for chemistry. So what I want you to do is when you use this approximation, because this math is much simpler, find x using the approximation. When you're done, take X, divide it by the initial concentration, and ensure that it's 0.05, less than 0.05. 0.05 would be the decimal version of 5%. So if I take X, once I found it, divide it by the initial concentration in this case, we'll see how that shows up, and I get 0.04, then I'm like, this is good. If it's bigger than 0.05, then I have to go back and redo the equation without the approximation. I'll have to use the quadratic equation and solve it. So that will save you the most amount of time. Start with a small x approximation unless there's something indicating you can't. And then check it, see, is it a valid approximation? If it is, move on. If it's not, go back and redo the problem using the quadratic equation. And I know I haven't shown you these expressions, but again, now we're going to go back and see where these expressions would come out from the ICE table. All right, so let's look at this particular reaction. I've left coefficients of 1. So we have, this is acetic acid, makes H plus C2 plus acetate ion. Note I have my reversible double harpoon arrows indicating this is a reaction in reversible reaction. It even gives me a K value. Kc equals 1.8 times 10 to the negative 5 at 25 degrees Celsius. So, and then it goes on to tell me the reaction mixture initially contains 0.2 moles of acetic acid, 0.2 molar. And then we would assume it didn't say anything about the products, but we can assume since it didn't say anything at the beginning of the reaction, initially it should be 0. So I set up and it asked me, what is the equilibrium concentrations of all the substances at this temperature? Okay, again, I begin with an ICE table because this is now going to be based off of how many moles of reaction react, and I don't know that. So I have a column for every substance in the reaction, one for my reactants and one each for my products. I write down my initial concentrations. In this case, for the products, we'll assume it's 0 because it hasn't started. Since the coefficients are 1 for each thing, for the reactant, the change would be minus X. For the products, it's going to be plus X. And now I can add these. Well, 0 plus X is just X. 0 plus X is X. But for the reactant, 0.2 minus X would be the equilibrium value. Now, at this point, this part comes later on. So I have these 3 values. X will be what I'm going to call the equilibrium concentration of hydrogen ion and of acetate ion, and 0.2 minus X would be the equilibrium concentration of the acetic acid reactant. So I set up, now I go back, I set up my K expression from the reaction. Kc equals concentration of H plus times concentration of acetate ion divided by concentration of acetic acid. The fact that you don't know that these are acetic acid and acetate ion, that's fine. It's just easier for me to say the chemical names from looking at the chemical formulas. All right, what we do now is we take these expressions from the E row of the table and I place them in. This would be X. This would be X, so on top I get X squared. And on the bottom I get 0.2 minus X because that's what the equilibrium value for the reactant is. Notice that this now looks like what we were talking about on the last page. I'm going to make the equilibrium expression the small x approximation. I'm going to say I think X is much less than 0.2, so I'm going to neglect it in the case just in the denominator where it's being subtracted. Obviously, we leave these X squareds on top. So now this reduces to X squared over 2. I multiply both sides by 0.2, and that would get me what X squared is, and I take the square root of the equilibrium constant times 0.2, and I get 0.0019. So this is what X is if this approximation is true. I want to now go back and test the approximation. X is 0.0019. I'm going to divide it by the equilibrium concentration, the initial concentration, 0.2. If I do that, the ratio is 0.009. 0.009 is less than 0.05. That means it was 0.9% instead of 5%. So it's much lower. This is a safe approximation. That means I can assume that X is 0.0019. But I'm not done. Now I go back and I plug in 0.0019 for X. My equilibrium concentrations for H plus and acetate ion will be 0.0019 molar each. And for the acetic acid, it'll be 0.2 minus 0.0019, which ends up being 0.198 molar. So notice very little of it changes. Started at 0.2, it ended at 0.198. So this would be how we go about finding equilibrium concentrations if I know the initial concentrations and the equilibrium constant value. This one's a little bit more tough. If I consider this reaction of N2O4 makes two N2O2s, and I know its K value, it's given to me at a particular temperature, and I'm told its equilibrium, its initial concentration, N2O4 is initially 0.1 molar, I can calculate this one. Again, I set up an ice table. Here's my reactant. Here's my product. Initially, I have 0.1 molar of the reactant. I have 0 of the product. Since there is a coefficient of 1 on the reactant, it's minus X for the change. Since it's a coefficient of 2 on the product, it's plus because it's a product, and 2 because there's a coefficient of 2X. I simplify these. 0.1 minus X would be my equilibrium concentration for the reactants, and 2X would be my equilibrium concentration for the product. Now I go back, I set up Kc. My K expression would be my product raised to its coefficient of 2 divided by the reactant, concentration of the reactant. Now I plug in my equilibrium values from the expressions from the equilibrium row of the table. 2x squared over 0.1 minus x. I will try the approximation method, in which case I say this minus x being subtracted from the 0.1 is so small, then let's say it's just going to be 0.1. I do a little math. I multiply both sides by 0.1. I, figure out 2x squared is equal to 4x squared. So then I have to divide both sides by x to get x squared. Then I take the square root. So I still got to do some math, but it's easier math than quadratic equation. So if I did this method, I would get 0.09. 0.0949 as my equilibrium, as my moles of reaction. I want to test that. Is 0.0949 divided by the initial concentration of 0.1 less than 0.05? No. It turns out it's 0.94. Not okay. So that's saying this is not less than 5%. A significant amount of the reaction reacts. So I now go back and I redo it with quadratic. If I take this expression, I multiply through to get 2x squared would be 4x. 2x in parentheses squared is equal to 4x squared. And then I multiply through, I collect all the like terms, I end up with this quadratic. 4x squared plus 0.36x minus 0.036 equals 0. Now that I have it in that format, now I can use the quadratic equation, negative b plus or minus b squared minus 4ac, all divided by 2a. So notice that now I'm taking these coefficients not in the reaction, these numbers in this expression, quadratic expression. Solve for it. Note that if I were to, and by the way, once you get to this, when you're doing homework, you can use a solver or something to just, once you have it into this format, to get these, to kind of save yourself a little time. You do need to be able to use this on a test. I would end up with two roots, 0.060 and negative 0.15. But notice, if this was negative 0.15, and I started with 0 plus 2 times negative 0.15, this 2x would end up being negative 0.3 for the equilibrium concentration. I can't have an equilibrium concentration that's negative. Therefore, I'm saying the negative 0.15 is not a possible answer. Thus, x is equal to 0.06. Now I put 0.06 in here in place of x. 0.1 minus 0.06. For here, I have 2 times 0.06. Here's how I get my final concentrations. My equilibrium concentration for N2O4 would be 0.04 molar, and my equilibrium concentration for NO2 would be 0.12 molar. A lot of math, but if you practice through, not that bad.